Let's look at some example problems involving acceleration, and these will be the constant acceleration equations of motion that we'll be using in these problems. The first one seems kind of odd. It's also not exactly well stated, but it's as it came out of a textbook. Galileo, while rolling a ball from rest down an inclined plane, observes that it rolls 1 cubit, the distance from the elbow to the fingertip, as he hums 10 beats of his favorite tune. How far has the ball rolled when Galileo has hummed 20 beats? Okay, this sounds pretty weird, but Galileo was the one who investigated accelerated motion early on. He's probably the first one who quantified it and found out that it had a t squared in the relation. Also, he was a trained musician. Virtually all well-educated people were at the time. Galileo's father was a famous lute player. That's an instrument similar to a guitar, or at least it has strings. So he was a trained musician. And at the time of Galileo, there were not decent clocks. However, Galileo found that if you made a pendulum of a particular length, it would swing at the same period as another pendulum of that length if it was a simple pendulum. And so he could have had a simple timekeeping device, and you can imagine him using a pendulum as a metronome, and imagining him listen to music. If you've taken music classes, you may have heard of 16th notes, which is a way of dividing a single beat into 4 parts. So it's like 1 eana, 2 eana, 3 eana, 4 eana, 1 eana, 2 eana. We have to make a couple of assumptions here. We need to assume constant acceleration. And actually, for a ball rolling down a plane, for a while that'll be the case until it starts going fast, and then friction will start to play a role. We know it goes 1 cubit as he hums 10 beats. How far is it going to go when he has hummed 20 beats? Or how far will it have gone? Constant acceleration, we can write down the equations of motion. X equals x naught plus v naught t plus 1/2 at squared, and v equals v naught plus at. Since we're kind of given some time here, I don't think we need to worry about the v squared minus v naught squared equation. Also, it says from rest. Okay, that tells us that v naught is equal to 0, and we get to choose where x naught happens to be, and let's just say x naught is 0. That's the starting point. So we can do that. Well, when we do that, this equation just becomes this. Let's do this in the right order. X equals 1/2 at squared. The distance traveled is proportional to the square of the time. We know that when the time is 10 beats, the distance traveled is 1 cubit. So these are weird units, but that's okay. We can deal with them. 1 cubit is equal to 1/2 times a times 10 b's. I'm going to use b as the abbreviation for beat here. And we can do a little bit of algebra and find out that the acceleration in this case is 1 cubit times 2, that'll make it 2 cubits, divided by 10 b's squared, and what you end up with is 2 cubits over 100b squared, or I'm going to leave this as a fraction since the units are so goofy. 2/100ths of a cubit per beat squared. All right, well, that's a unit of length. This is a unit of time, and it's just like meters per second squared. So cubits per beat squared. Pretty weird. So how far is it going to go in 20 beats? All right, well, x is going to equal 1/2 times 2/100ths of a cubit per beat squared times, well, we're going to have 20 beats this time when we square that. All right, we can do this in our heads. When you square 20, you get 400. The units here will be beats squared. The units of this, the beats squared, will divide out with the units of that. So I'll have 400 times 2 divided by 100. Well, that's 800 divided by, excuse me, yeah, 8, whoops, no, there's a 2 down here too. Okay, those 2's will divide out. So anyway, we'll have 400 divided by 100. That's 4 cubits is what we end up with. Now, there's an easier way to do that. When I look at something like this and I see, okay, the distance traveled is proportional to the square of the time. If it goes 1 unit in 10 beats, if you double the time, when you double something, you get a number and square it, you get a number 4 times as big. So it'll go 4 times it as far in twice the amount of time. If you tripled the time, say 30 beats of his favorite song, it would go 9 times as far because it goes with the square of the time. So anyway, there's an odd little problem, but we had to assume constant acceleration here. Hey, here's another interesting one. An automobile traveling 56 kilometers per hour is 24 meters from a barrier when the driver slams on the brakes. The car hits the barrier 2.00 seconds later. What was the automobile's constant deceleration before the impact? And how fast was the car traveling at impact? Well, first thing I'm going to do is convert this into meters per second because I'm given a distance in meters and we're not dealing with hours here, we're dealing with seconds. So I'll do that quickly. Turns out it's 15.6 meters per second is that. We're going to assume, oh, it says what was the automobile's constant deceleration before impact. So we're assuming it's constant acceleration. Even though it's got a DE on there, it's still an acceleration. We're going to use constant acceleration equations. X is equal to x naught plus v naught t plus 1/2 at squared. I know v naught, it's the 15.6 meters per second, so that's good. Let's see, x naught. I'm going to let that be the point at which the driver slammed on the brakes. That's usually our choice to decide where that is, so I'm just going to let that be 0. X naught is equal to 0, which turns this equation into x equals v naught t plus 1/2 at squared. Now, in this problem, the only thing I know is v naught. However, I know the position when t is 20 or 2.00 seconds. And I'm going to state that in a sentence here. When t equals 2.00 seconds, x is going to be 24.0 meters. The car will have traveled to the barrier at that time. So if I look at this equation now, knowing v naught, I know x and I know t. The only thing I don't know is a. I can find the acceleration doing that. And once I know the acceleration, I can do things like, well, that's the first question actually, but I can do things like how fast was the car traveling at impact. I can use the constant velocity equation or constant acceleration equation involving velocity, which I forgot to write down. That's the v equals v naught plus at equation. I can use that to solve part B. So let's go dive into part A here. First, I'm going to solve things in variable form. And I want to solve this equation here for a. So start by having x minus v naught t is equal to 1/2 at squared. Let's see, it's just a that I'm after. Multiply both sides by 2 and divide by t squared, and I'll get a is equal to, by the way, I tend to do 2 algebra steps at once when it's something like this. So if you need to do it step at a time, don't feel bad. I also have to be careful and slow down once in a while because my occupational hazard of talking and writing at the same time, I can sometimes make mistakes. So multiply both sides by 2, divided both sides by t squared. Okay, that's good. Now I just plug in the numbers I know. 2 times 24.0 meters is where the car will be at this time. And I'm keeping units with every number that has them. V naught is, I'm going to double my parentheses here, that's the 15.6 meters per second. The t that I multiply it by is 2.00 seconds. And then I divide by 2.00 seconds squared. So you'd have to be careful punching this into your calculator, although it's not quite as bad as it looks. I just put parentheses around these for making it easier to read. But I end up with an acceleration here of minus 3.60 meters per second squared. Now, let me show you how I got the units. On top here, I've got meters there. Here I've got meters per second times seconds. The seconds will divide out and I'll have meters here, so the whole numerator has the same units, which it must. You can only add or subtract things that have the same units. And then I've got meters on top. On the bottom I've got seconds, but they're squared, so it's meters per second squared, which is what I'd expect for an acceleration. So there's the acceleration of the car. It probably didn't have the greatest tires, because if you slam on your brakes with good tires, you can get a higher acceleration than this typically. Or maybe the road was wet. How fast was that car traveling at impact? Well, for part B, I'll use the velocity equation. V equals V naught plus AT. My V naught is the 15.6 meters per second. Plus the acceleration is the negative 3.60 meters per second squared, and the time it took to hit the barrier was the 2 seconds that they gave us. So, and when it hit the barrier, it was going at, let's see, 8.40 meters per second. I can kind of do that in my head. This would be minus 7.2 meters per second. Yep, 8.40. Actually, I can't do that. It's going to be 8.4 meters per second, because the uncertainty here is in the tenths place, and this I could write it so it's got it in the hundredths place, but when you add or subtract things, it shows up in the place of the least precise number. So that's where it's going to be. So anyway, that's how far how fast the car was going when it hit, which that's down about 17 miles an hour or so. So still going fast enough. With the current car repair prices, that would probably be a totaled car, depending on how sturdy the barrier happened to be. We had to go through a bunch of different things on that problem to solve it. And this is typical, that you have to somehow piece together a solution, but the way to start is always by writing down the constant acceleration equations and then go forward from there. During the first 2.50 seconds out of the starting gate, a skier slides 10.0 meters, assuming uniform acceleration. Okay, uniform acceleration, that means constant acceleration. Find the time when the skier reaches a speed of 30.0 meters per second, and then how far from the starting gate is the skier at that time. Well, uniform acceleration, then the equations of motion are going to be x equals x naught plus v naught t plus 1/2 at squared, and v is going to equal v naught plus at. Now, the skier is going out of a gate. They go when the bell rings or whatever it is that they do to start skiers, maybe lights flash or something, give them a green light, but they start from rest, and I'm going to let the location of the gate be x naught, be 0. So x naught is equal to 0 and v naught is equal to 0. That means this term's gone, this term's gone, and the position as a function of time is just 1/2 at squared. Then this equation becomes v is just going to equal at. So my equations simplify when I have something starting from rest and when I can define the initial position to be 0. So this isn't so bad anymore. Now, assuming find the time when the skier reaches a speed of 30 meters per second. Well, I don't know the acceleration yet, but I am told that during the first 2.50 seconds out of the starting gate, a skier reaches 10 meters. This is something like a previous problem where at some particular time I know what the position is, and so I can use that to figure out the acceleration. So I can say when t equals 2.50 seconds, the x is equal to 10.0 meters. So I'm going to use that bit of information to figure out the acceleration. And sometimes we have to do that. So anyway, solving this equation for acceleration, I'd multiply both sides by 2. The acceleration is going to be 2 times x divided by t squared. So that'll be 2 times 10.0 meters divided by 2.50 seconds squared. And I get that the skier's acceleration is 3.20 meters per second squared. Okay, then I can answer question A. Find the time when the skier reaches a speed of 30.0 meters per second. Well, here I know the speed, I know the acceleration, and I want to find the time it takes to reach that speed. This is a velocity equation, and so I know the velocity, I know the acceleration, I'm just trying to figure out the time. So v equals at, and so the time is going to equal v over a, which is 30.0 meters per second divided by that 3.20 meters per second squared. It may seem like it takes them a while to get there. I get 9.38 seconds for that. Divide a meter per second by a meter per second squared. Flip the bottom, I'll show you that. Meters per second times seconds squared over meters. The meters divide out, seconds squared over seconds equals seconds. So that's why that is. Okay, well, it takes almost 10 seconds to get there, but 30 meters per second. This is a human being on skis we're talking about. 30 meters per second is between 60 and 70 miles per hour. That'd be pretty exciting to go from 0 to more than 60 miles an hour in that period of time. So now we know how long it took them to get there. The second question asks, how far from the starting gate is the skier at this time? So I'm going to do this two different ways. And the first way, since I know the time and I know the acceleration now and I know the equation of motion, I can just do this. X is equal to 1/2 AT squared. X is going to be 1/2 times 3.20 meters per second squared times 9.38 seconds, which I square, and I get a distance of 141 meters. So that's one way of doing it. The other way is, they might have stated this, they could have skipped part A and said, how far from the starting gate is the skier when their speed is 30 meters per second? And this doesn't ask time or anything like that. You can use this equation to get it. It's the other equation, v squared minus v naught squared is equal to 2 times a times delta x. Still v naught is 0, so you can have v squared equals 2a delta x, or delta x is going to be v squared over 2a, which is 30.0 meters per second squared divided by 2 times 3.20 meters per second squared. And if you plug the numbers into this, turns out you get 141 meters per, or just plain meters, excuse me, meters squared per second squared divided by meters per second squared gives you meters. So comes out the same way. By the way, this equation, I've written it as a v naught squared, but it actually works even if you're not talking about time 0, because it doesn't have time 0 in here. And you can sometimes just think of this as v2 or v final squared minus v initial squared equals 2a delta x. And so you can use it for any interval as long as there's constant acceleration.